Hello, today we're going to talk about lab number 6 on instability and advection. Now, I originally was going to make this video in a different setting, but I ended up doing it at work um, because it was due to convenience and certain circumstances, but we shall proceed. Serving you from Chipotle, serving you up a weather forecast here at Chipotle. Seems appropriate. Now, the lab at the beginning, we're going to talk about um, the stability. So we're going to go over stability. That's what I'm going to go over right now. And we're going to use the 850 millibar and the 500 millibar chart. We're going to be analyzing Omaha, and we're going to predict um, what the if it's gonna be unstable or stable um, within 24 hours. So we're gonna have a 24-hour prediction. And how we're gonna do this, we're gonna take the temperatures using the isotherms, looking at the isotherms. Looking at the temperatures on both the 850 and the 500 millibar chart. And if the and we're gonna subtract it from 850 temperature from the and subtract 500 from the 850. And then if it's 25 plus the difference, then it is unstable. So then that calls for precipitation, um, and there's lifting in the air. So if it's unstable atmosphere, there's gonna be lifting in the air, and that's how we see. So let's start at using the 850 millibar chart at 12Z. Okay, so we check out Omaha. Right now it is negative 12 Celsius. This map is in Celsius. And then we go down to the 500 millibar chart. It's at 25, negative 25, sorry, negative 25 Celsius. So we would take the negative 12 and subtract negative 25, and we end up getting 13. So then is it unstable, or yes or no? No, it's not, because it has to be at least 25 or above to be considered unstable. So now we are going to go on to the predictions. So how we predict for the 24 hours? Now, let's go up. We would use both these charts together. And let me go back to my notes real quick. So what we would do first is take the average temperature using the isobars around the area. And we would, if let's say there's 3 isobars, we would get those isobars, and let's say they add up to 90. And we would divide it by the 3, and it would be 30. So then that would be the wind speed that we would take and plug into the equation. So then we would take that wind speed times it by 24, and that's going to give us a distance. So whatever number it is, let's make up a number. Let's say it gave us 1,000. That's the distance of miles that we're going to use to trace the speed for tomorrow. And how we would, like, what direction we would go? We would go the direction of which the isobarbs are coming from, the wind is coming from. So let's say it's a west wind. So then we would go retract to the west 1,000 miles, and then the closest station model will tell us what the weather is, and that the temperature is, and that temperature is going to be the temperature that's going to move, the air that's going to move um, towards, and it's going to replace the temperature in 24 hours of the current area that we're trying to predict for. So let's say if it's test we do all that and it ends up saying negative 10 Celsius, and right now it's negative 8 Celsius. Well, right now it's negative 8 Celsius, but it's going to eventually be negative 10 Celsius in 24 hours, and that's how we um, trace for track instability, and we look for we predict for the future using these equations. So let's do it now. So we talked about how to do it, but let's actually put it into play. Let's use this knowledge we have, and not just have it as a theory, but actually put it into work. So we have the 850 and the 500 millibar chart we've seen here. So let's see. So let me go back to my notes. So we were looking at the 850 map in Omaha, Nebraska, we're predicting for. So right now it's at negative degrees Celsius, right? We see that. And next to it, we see a barb. Um, the barb is it looks like it's one full line and a half line. Now that indicates that that's equivalent to about 15 knots, so 15 miles per hour. Okay, so that's good. And then next to it, there's another knot that's two and a half lines, which is 25. So I'm gonna take the 15 and the 25. And then there's another one next to it that's three lines, so that's 30 knots, and that's 30 miles an hour. I add all those up, I get 70. Now I divide those 70, since I have three of them, I divide them by three, and I get 23.33. Now I'm gonna plug that into my equation, times it by 24 hours, and I get 559.92 miles. And then we see that most of these barbs, they're coming, they have the wind coming from the southwest. So now we're gonna move to southwest, 559.92 miles per hour. Now, and then I already did this prior, the calculations and everything, um, and I traced it out, and it ends up taking us, if we go southwest from our point where our starting point from Omaha, Nebraska, southwest, it takes us to the closest station model. It ends up being -2 degrees Celsius. So that will travel eventually towards Omaha, and so that's how we did it for the 850. Now we're gonna go to the 500 millibar chart. Okay, we're in the 500 millibar chart, looking at Omaha, -25, right? So it's -25. We see that, and then it's the station model has one, two, three, 4.5 lines on the ISO bars, right? And barbs. I can't tell if it's ISO barbs or bars. I got to check that out. But on the station model, it tells us the wind direction. It's coming from the west, so we're gonna move eventually from the west. We're gonna trace the from the west. So we have the 45 right there, and then we have the next station model has we have a station model that has two, it's 2 knots, and we have another one that's 2.5. So we have a 20, a 25, and then we have a 45. I'm adding all those together, I get 90, and I'm gonna divide that by three because it's three station models, and that gets me about, well, it gets me exactly 30 knots, and it's all coming from the west wind, from west winds. So we take that, so we're gonna move that, plug into the equation. We have 30 is our wind speed, so 30 miles per hour times 24 equals 720 miles. And we're gonna go, okay, so we're gonna retract, we're gonna go trace this to the west. So from where it's positioned, we're in Omaha, and now if we go west of that, 720 miles, we end up finding a station model that is -20 Celsius. So that's eventually going to move on all the way to Omaha, and that's going to replace the temperature in 24 hours. And so in 24 hours, it's going to be -20 Celsius. So we're doing good. Now we're going to the next part, and this is all filled out. So these maps I filled out on a piece of paper. I couldn't print it out, but I filled it out on a piece of paper and I sent it in your email. So you find the notes and the calculations to all that. Now we're gonna move on to, I believe, question 2, or the second. It's actually the second map. We're gonna actually use all these maps, these 4 maps, and we're gonna predict. So the objective is to predict stability at 12Z, 12 February 2008. How we do that? We would fill this chart out, but I will explain right now the process. So first we're gonna look at, let's go all the way up here at 0Z. So 0Z with a 12-hour forecast. So now we're gonna look at Omaha, where it's stationed, okay, where it's positioned, and where how the isotherms lines equal temperature line up, where they lay on top of Omaha, Nebraska. Now it looks like the isotherm on top of Omaha, Nebraska is at 850 millibars. I put down as 12.5. So 12.5, okay. Looks about right. A little, And then we're gonna put that in, so that would be in the table. So we're gonna work on that too. So okay, 12.5 we have for A50, and then we go to 500 millibar. I put it down as oh, actually it was negative 12.5, sorry. And then at 500 millibars, I have it down as negative 25, so negative 25 Celsius. At 500 millibars at 0Z. Now we take the negative 12.5 and subtract negative 25, and we end up having 12 point 12.5. So that is stable because it's if it were unstable, then it would be a 25-degree Celsius difference, 25 and above. But it's 12.5, so it's less. So then we're moving on to the 12-hour forecast at 12 at 12Z. Okay. So at 850, we see that I have it marked down as a negative 15 degrees Celsius isotherm. So that's how about how warm it is there. What is how warm it is there at Omaha, Nebraska. And then we move on to the 500 millibar chart for the 24-hour forecast, and we are at um, it's about I put it down as um, negative 28.75. Okay, so we take the 15 from the 800 millibar, negative 15 from the from the 800 millibar, and subtract the 28 negative 28.75 from the 500 millibar. That gives us 13.75 difference. So that makes it a stable atmosphere. So no rising of air there because it is under 25 degree difference, so it is stable. Okay, so then we have this part. So that's basically it for finding out stability. And there's good demonstrations with those maps. Now, and those tables are filled out again in my notes that I sent you, a picture of them. And now moving down to part two on temperature advection. Now we're gonna have a little brief run through of temperature advection and demonstrate the knowledge learned. And then you give us here the just how to go about it. This is really helpful. I almost looked over it, but once I seen this, I wrote it down. So then it gives us the little help on how to go about it, what units are, knots interchangeably. Okay. We go down. We're gonna use this map, these surface temperature maps, and to help us figure out. We'll just use this in play. Let's see. So for question one, it says, what type of advection is occurring across the blue oval from west to east? And I put down cold air advection. And I'm explaining why. Um, so what I did, so I used the formula that you gave us to find advection. And first, I looked at around the area that is circled. I checked for the wind speed, and I ended up deciding the average wind speed is 20 miles per hour, and then I put that in the equation, and then I times that by 15 15 degrees Fahrenheit, which is the change in temperature. Looking at the isotherms, and I seen that it starts from 60, around 60 to 85. So that was the change in temperature is 15 degrees, and then so with 20 times 15 and divided by 200 miles, which is the distance, I ended up with 1.5 um, degrees Fahrenheit, and then I put that on top of the hour because that's what you gave us on right here to reduce the fraction in advection formula to the temperature on top of hour. So then I did that, and I ended up with 1.5 over the hour, and that um, calls for significant advection because we need at least 0.5 or more to be considered per hour to be considered significant advection. So then I've said yes because 0.5 plus is considered significant advection, and we have at least that. So then now we move on. Let me see. Wait, let me just check if I didn't miss anything. No, we have it all down, so we're good. And now we are moving down to question number two. So for question number two asks, what type of advection is occurring across the blue oval from south up to north? And I said warm advection. Now, first I checked out the isotherms, and it ended up being, so what I put down is that there was a 10 degree change in temp. Now let's look back at it. Let me see, make sure I did good. Okay, so we start from the brown all the way to the yellow iso area, and so it's 100 to 90. So that's a 10 degree change in temperature, and we know that it's coming from south to north, and the south is more hotter, 10 degrees than the north. So eventually it's going to be 100 degrees. It's going to change 10 degrees, and that is a warm air advection that is rising horizontally in the atmosphere towards Omaha, Nebraska. So we have that. So, and then we see that the temperature is 10 degrees. I mean, the wind speed is 10 degrees. So we times the 10 degrees, miles per hour, 10 miles per hour times 10 Fahrenheit. Divide that by 200, and we end up with 0.5 Fahrenheit over the hour, so per hour. And that ends up being significant advection because we know that we need at least 0.5 a change in temperature per hour to be considered significant advection. So then yes, number two is significant advection as well. So now we're off to number three, question number three. So question number three says, what type of advection is occurring across the blue oval from south to north? So again, from south to north, we're moving. Um, now, I put down that there is no advection. And the reason why is if we go to the map, so we see the blue oval, right? And it's within the same isotherm. There is no change in isotherms cutting across. There's no wind cutting across the isotherms, which would um, change or rise the wind. And we see that it doesn't really matter the wind speed because there's no change in temperature to give us advection. So the wind speed is, well, it is zero. So, but the wind speed, we might as well talk about it. I averaged it out. Let's just say about 10 miles per hour. We times that by the zero and divide it by 200 miles an hour. No matter what, we get zero. Zero times anything is zero. Times it by zero. So then we ended up with 0 degrees Fahrenheit over 1 hour, and that calls for a stable atmosphere. It is not unstable. There is no rising of air in the atmosphere. It's no because 0.5 and up is considered significant advection, and we have not met that. So that is a stable atmosphere. And that is all for today. We talked about temperature advection and instability in the atmosphere. I hope this video makes you well, and I hope you have a good day, and God bless. Take care. Hope you enjoyed.